Welcome back. We are now at lecture 22 and we will spend quite a bit of time on the chemical potential mu. Uh, what we are going to do today, and it's a pretty important lecture because this is a lecture where we introduce the fact that the thermodynamic process can happen with an exchange in particles and also a change in the number of particles. So of course, we understand that this will apply to chemical reaction, but also other effects where the number of particles can change and also or transform from one particle type to another one. So let's try to go back to where we started, which was to write the internal energy, or in fact the changes in internal energy as an exchange or transfer of heat and a transfer of work between a system and its surrounding. So this is really what we started from. Uh, the bar in the D on the right-hand side, they are there to remind us that we have we have inexact differential. In other words, the way heat is transferred or work is performed depends on the path that's taken, unlike the internal energy that's a function of state, and therefore can be written as an exact differential. Okay, so these are things that we've seen quite a few times in this course so far. So now imagine that you have this very simple reaction. Um, how do we account for this using the framework that we have developed so far? Well, it is difficult to do because we are changing the number of particles. So we do not have a term in which the number of particles has changed. In fact, we have used density, lowercase n, and the number of particle n, uppercase n, uh, but we always considered they were constant. We never really worried about taking differential or changes. We always expected to be constant so far. Well, in this lecture, we are going to allow for those changes. And this is how we are going to introduce what's known the chemical potential. So basically, what's important for students is to remember that when you talk about change in the number of particles or exchange of particles, you should always automatically think about chemical potential. This is one thing that's important. So what I'd like to say at the outset of this lecture is that it's going to be fairly heavy with formalism and maybe a lot of equations that are going to come from different parts of the course. As always, try to remember that what we are trying to understand first and foremost are the concepts. Once you understand the concept, which are of course the hard part to understand, then you can focus on the math. Um, it's very important not to think, oh, I don't get the math, therefore I give up. Or even worse, I get the math and therefore I'm happy. Now, what's important is to understand the concept first and then do the math. There are a lot of equations. There is no expectations to know all of them by heart, but at least to understand where to find them and also understand the meaning. So let's try to do this, and let's start from right away with the definition of what the chemical potential mu is. And it is just as written on this slide. It is the amount of energy added to a system when an additional particle of a given type is added to it. Okay, so that's a little bit, that's not a super clear definition yet, until we are going to see an example. So we'll see what it means. It means actually sometimes here it's an equation that explains it. So mu basically is going to be the energy that's added to a system when one particle is added to the system. Okay, so of course if we have more than one particle, or if a different number of particles than one, we are going to introduce the number dn, which is a change in particle. So basically this here is an energy that's added to the internal energy that corresponds to a change of particle n. So that means that the internal energy now can be endowed with an additional term, which is mu dn. So we find the two terms that we had before, right, which are the sum of the heat exchange and the work exchange. And remember, I can only say that this is the heat and this is the work for a reversible process, even though the sum of the two are indeed the heat and the work performed. And so we add this term here. So this term is actually going to help us consider a change in the number of particles. And you will see, of course, that this mu dn is going to trickle down in all the functions of state that we've discussed, including the entropy, including the Gibbs energy, including the Helmholtz energy, including the heat, the enthalpy. So all those things are going to be included, and of course we will be able to apply everything we've learned so far, in particular the first two laws of thermodynamics, to see what is the effect of the entropy wanting to be maximized on the terms mu dn. So one thing I should also mention before we move on is that if you want really to be a purist from calculus, this dn here is kind of a strange beast, because n is an integer. So the differential of an integer here is kind of weird, because dn cannot be infinitesimally small. So let's not worry too much about this. We'll be careful when we have to be careful about the math. This is almost symbolic at this point. This dn here is going to be very small when the total number of particles is huge. So for example, if you have a change in one particle out of a mole, that's 1 out of 10 to the power 23 particles. dn can be considered infinitesimally small. But again, this is an abusive definition. But just like to be clear that I am well aware of this. Okay, so let's go back to this. Let's go back to the internal energy as we just defined it, and let's try to see what we can get from this. First of all, since U is an exact differential, we can now say that the natural variable for U is S, V, and N. And that means that this term here can be written, so the plus mu can be written as the partial derivative of U with respect to N at constant entropy and volume, just like what we did before when we looked into the lecture on the thermodynamic potential. This is the same idea mathematically. But again, mathematically, there's no problem. But the problem is, even though we can imagine a reaction or can imagine a process where we keep the volume constant, even though chemists usually prefer to keep the pressure constant because they work at atmospheric pressure, so even that is not great. But what's worse is S. So how do you perform an experiment at constant entropy? Well, there are ways to do it, obviously, but this is not the most convenient. A chemist would prefer to do it at constant temperature or constant pressure. So, of course, this is the same philosophy, I would say, that same strategy, should I say, that we've used before. We are going to introduce other thermodynamic potential where the natural variable, instead of being S and V, will be SV and N, sorry, they will be, for example, T, P, and N. And you remember what they are. T, P, and N, that will be the Gibbs energy. If you were doing S, P, and N, you would be the enthalpy. And if you were doing T, V, and N, that would be the Helmholtz energy. So these are things that are easy to remember just because we understand in what context they are being used. But anyways, we are going to go into that. So we are going to introduce, we are going to reintroduce, I would say, the thermodynamic potential, but now including the terms mu dn. And there is no difficulty really, because remember how we introduced those thermodynamic potential. We introduced the Helmholtz free energy as being U minus Ts, and that definition still holds. It's just that U has changed. And then, of course, also the Gibbs energy, which was U plus PV minus Ts. And remember what we did this. I'm going to remind this to you again so that it's not a mystery. We basically want to get rid of the PDV and replace something with something dP, because the Gibbs function is used at constant pressure. Therefore, we add PV. So that means that this dPV is dPV plus VdP. So we get rid of this. And same thing for the TS. We do not want to consider a change in entropy, but instead of temperature. I've done all this in detail in the previous lecture, but I'd just like to remind you, because I have heard that teaching is repeating. Let's keep moving. Okay, so we have this here. And first of all, of course, we can calculate the differential df. And remember, the reason why we can't calculate the differential f of f is because all those thermodynamic potential will be zero and actually will be minimized at equilibrium. So of course it makes sense to calculate df because at equilibrium df will be equal to zero because you have reached a minimum, right? And again, I just like to repeat this one more time. The principle that says that df will reach a minimum, it's an embodiment of the first and second law of thermodynamics. Good. So df can be calculated like this, and the first two terms should be familiar to you. These are the same that we've seen before, but of course, we still have mu dn right here. So we have mu dn, and they come simply from the du that we've calculated. Nothing really spectacular. We can do the same for g, for the Gibbs function. And one more time, the first two terms are the familiar ones, and the last term is mu dn, again, coming inherited from the du. So far, so good, nothing really complicated. Bear with me, things are going to become more complicated, but this is so far very, fairly straightforward, okay? Now, of course, these two definitions, because those two definitions are useful because these are the exact differential, and again, we know that these terms here can be calculated as partial derivative of the starting function with respect to n at different constraint. So this one here is calculated when t and v are constant, so that those two terms cancel and we just have this left. And this term here is calculated when these two terms are constant, p and t, and therefore that is another definition of mu. So when I say another definition, I'm not saying that these values are different. They are all calculated, they're all the same, but they can be obtained differently. So for example, somebody, let's say, imagine a chemical reaction that's performed at constant pressure and temperature. If the Gibbs energy is actually measured or one way or the other, as we've seen in the previous chapter, looking at how that function changes as a number of particle changes through the reaction will allow you to get the chemical potential. This is really what it means. So it's very important to try to read those mathematical equations within the context of translating them into plain language. It's very useful to understanding what they mean and also, of course, to remember what they are. So let's keep moving and let's try to get a little bit of a better understanding of what the chemical potential is. So this is what's important. That sentence is of course a summary of what we've said before. We know the first law of thermodynamics tells us that the total energy is conserved and comes in different forms, right? Work, heat, transfer, and things like that. Now, the second law of thermodynamics tells you in which direction a process works. So what's the equilibrium state? So let's try to see how we can apply this in this case. And of course, we know the goal is to maximize the entropy. So the maximize the entropy, and again, just as a reminder, maximizing the entropy is related to maximizing the number of to lead the process or the system towards a macro state that corresponds to the largest number of microstates. Right? This is the statistical description of the entropy. All this is compatible to one another. So now the question is, we have the entropy, which we can say that depends on a number of natural variables, and then we've done that in the previous lectures. But here, what we want to do is as a start, is to say that the entropy depends on U, V, and N. This is something I can certainly do. I usually did not bother with N so far because we did not consider N to be a variable. We considered N to be a parameter of the problem. Okay, so let's try to write the entropy, which is, again, remember, a function of state, right? This is very important to remember this. It can be seen as depending on U, V, N. In other words, I can write this. So this is just description and exact differential for 3 natural variables. There's nothing really complicated here. So let's try to see what this equation exactly is going to entail. So what we just saw is that du is TdS minus PdV plus the extra term I just added a couple of slides ago. So this is du equal TdS minus PdV plus mu dn. So that means I can write ds as being du over t plus PdV over t minus mu dn over t. I just rearranged this. So I like this very much because I can now equalize. I mean, I can look at the different terms before the first equation on this slide and the third one, and in particular, I can write that this is true, this is true, and of course this here is true as well. And these 3 equations are extremely important, and they will come in handy later. Because they allow me to get some complicated derivative, I would say, as function of variable that are more that we can have easier access experimentally. When I say complicated derivative, I'm not talking about the math, of course. I'm just asking how, for example, does the entropy changes with the total energy? That's not an easy derivative to do. How do you do this? Well, it's actually just 1 over the temperature if that derivative is calculated at the constant number of particles at constant volume. How does the entropy change? How does the entropy change when we change the number of particles? And when we change the number of particles at constant total energy at constant volume, that change is actually minus mu over t. And these are things that will come in very useful when we move forward with the mathematics here. Okay, so let's try to go back. Remember, let's try to keep our eyes on the price. The eyes on the price is to say how does the second law of thermodynamics, which states that ds is always positive unless you're at equilibrium, in which case it's 0. So in other words, the entropy tries to be maximized. How does that principle translate into a system when the number of particles is not a constant? So that's really what we are trying to do. Well, we've done a lot of work related to that so far. And for example, we've looked into the entropy as deciding how the heat is going to be transferred, which direction the heat will be transferred between 2 subsystems that have different temperature. In fact, this is even the first statement of the second law of thermodynamics, which is Clausius' statement that says that if there is no other processes involved, heat will always flow from the hot reservoir to the cold reservoir. That's actually the second law of thermodynamics. This is where we started from. So basically, we did this when we didn't have to bother with the change in number of particles. So let's remind you how we did this. And we calculated the total change of entropy of this system where we have 2 subsystems that cannot exchange any heat or work or anything with the outside. And so it's a closed system. And we've seen that the entropy was a change in the entropy here plus a change of entropy here. So this is mathematically written like this. And the question is what it is. Well, we know that the change of internal energy U1 is is the same. Everything that comes out of the first reservoir goes into the other reservoir. So in other words, if du2 is du, just as written here, because it's heat coming in, so it's positive, right? du2 is equal to du. Then du1 has to be equal to minus du2, in other words, minus du. So this is one of those things where signs are important. So if you have any problem with this, just rewind for a couple of seconds or pause the screencast and think about this. This is essential. Remember that the heat comes into with the arrow, the way the arrow is drawn here, heat is coming into the second reservoir, so du2 is equal to du. And of course, it comes out of the first reservoir, therefore, du1 is minus du with those signs. That doesn't mean du is positive. It just means that du goes along the arrow that's given here. Okay. Now, what's nice is that we do know these expressions. We just obtained them on the previous slide. And so that means that those expression is minus 1 over t, and it's, sorry, is 1 over t for both of them. So we obtain this. And the second law of thermodynamics tells us that this has to be positive. The entropy has to increase until it's maximal. Okay, so that's good because this equation actually just reconnect with the closure statement of thermodynamics. Indeed, look, if T1 is larger than T2, we know that the heat is going to flow this way. So in other words, du will be positive. When we say du positive, it means that it follows the arrow I started from. Okay, as you see this here, du has to be positive if T1 is larger than T2. Because if T1 is larger than T2, this term here will be positive. Therefore, positive times positive will be positive. It's great. Now imagine that T1 was smaller than T2, then it's a smaller, this term here will be negative in between the parentheses. That means that this has to be negative as well, so that the product is positive. So du is negative. In other words, it follows against the arrow that I started from. So again, heat flows from the hot reservoir to the cold reservoir. I'm spending a bit of time on this. I realize that it's a reminder, but it's very important to understand this because what's happening with the chemical potential is very similar. It's just that the processes physically are different. And finally, of course, what's important to realize is that if the two temperatures are the same, there's no flow of energy between them. There's no flow of heat between them at constant number of particles and constant volume, right? So there's no work involved, so it's good. I mean, it's good in terms of U. The change in internal energy are the changes in the heat transfer. That's what I mean. In that case, when the two temperatures are the same, the entropy ds is 0, so we have actually reached equilibrium. This is the idea. So in other words, the entropy has been maximized. So the maximal entropy is when we have the two temperatures that are the same. And I'd like to remind you that this is because this is the system where there are the largest number of microstates. Again, try to think about your cup of coffee in the morning. You put milk in it, and it's very unlikely the milk is going to stay on the top and the coffee is going to stay at the bottom. They're going to mix. And they're going to mix for the same reason as because the mixture has a much larger number of microstates than the separation of the phases. This is exactly what we see here. So after this reminder, let's try to move back into what about the price, as I mentioned a couple of minutes ago. And the price, well, as I said, it's closure statement of the second law. The price is this. So we have a slightly different setup. We have two reservoirs, but now the two reservoirs have different number of particles, N1 and N2. And what we say is that the energy to add a particle, the energy that's associated with adding a particle in reservoir 1 is mu1, and the energy associated with adding a particle in the second reservoir is mu2. Okay, this is the definition of mu1 and mu2. So very quickly we are going to suppose that the two temperatures are the same so that we simplify a little bit the discussion, but they don't have to be the same necessarily, but we'll do that. The question is, how does the number of particles exchange between the two reservoirs? How do we decide this? How does entropy, or the second law of thermodynamics, imposes which direction the number of particles change? The number of particle changes. Let's try to see that. So the math is exactly the same on the previous slide. So now the variable that changes for the entropy is N1 and N2. That's the number of particles on both reservoirs. Now you understand, of course, that the change, the dN1, okay, if we are going to change the number of particles so that things again are along the same direction. So if dN is a positive number, right? In other words, if it goes that way, that means that we have a reduction of the number of particles in this. So dN1 is minus dN, and of course dN2 is equal to dN. The number of particles that are added here is dN. I'd just like to make sure that you think a little bit about the signs. That just not take it for granted and just copy from the slides. Think a little bit make the effort to think about the signs when you write those equations. Okay, so this looks very complicated. Well, not quite, because remember that a couple of slides ago we calculated those derivatives, and they were related, if I remember well, by minus mu over t, something like that. In fact, it was minus mu over t. That's exactly right. So, but if you don't know, go back 2 slides, and these are derivatives were calculated by simply um, comparing ds as an exact differential, and what we got ds from using the expression for du. That's what we did. So we end up with this. And again, we know the second law of thermodynamics is still valid, obviously. That means that the entropy has to increase or equal to 0 at equilibrium. Okay. Very good. So now let's try to understand a little bit this the same way we did before. Just to simplify, we are going to suppose the temperatures are equal so that we don't have to worry too much about this. Suppose they are equal. So if mu1 is larger than mu2, okay, the number of particles is positive. So if mu1 is larger than mu2, those particles are moving away. Okay, so those particles, the particles are moving away from the reservoir when it costs more energy to put them. Right, that's basically what it means right here. Okay, they're moving from here to here. Now, if dn will be negative, if it's the other way around. Now, that's very interesting, because that means that it's a little bit as if mu1 and mu2 had a similar behavior as t1 and t2, and so that's good. But let's try to be careful, because in the previous slide, and I'm actually going to go backward a little bit, just because it's important to see the difference. We had minus 1 over t1 and plus 1 over t2. Remember, there is a minus 1 over t1. Okay, and we saw all this. And so in this slide, we have mu1 over t1. So you could say, well, mu1 and t1 have the same effect, and they do. Is because what you have to compare is mu1 and 1 minus 1 over t1. What I'm trying to say is that you would think that mu1 and t1 should have opposite effects, since one is in the numerator and the other one in the denominator. But there is also a sign difference. So basically, indeed, when mu1 is large, minus 1 over t1 is large when t1 is large as well. So in other words, they play the same role. Okay. So again, try to think about that. If you want to draw the comparison, this is important to do that. So we've seen this. And of course, the number of particles dn will be equal to 0. So in other words, there will be no longer exchange of particles here when mu1 is equal to mu2. So in other words, the system is behaving in such a way, that at the end, in equilibrium, the chemical potential on both sides will be the same. So this is not very surprising, because again, mathematically, the T1 and mu1 have the same effect. So just the same way as a system will evolve to make sure that the temperatures are uniform, the system will also evolve due to the second law of thermodynamics to such a way that the chemical potential on both sides are the same. And one more time, this is because that particular configuration consists in the largest number of microstates. So in other words, the one that maximize the entropy. So there are subtle effects here. So I'd like you to make sure that you understand this before you even try to move forward with the math that we are going to do now. So let's try to see the chemical potential of an ideal gas. And an ideal gas has been our friend so far, because we know quite a bit about it, and it's maybe one of the simplest ones. So we have mu is equal to this derivative, again, as a function of Helmholtz energy. And again, we use this because we like the constraint we can impose is volume as temperature. And in the previous lecture, we've actually calculated the Helmholtz free energy here. And then all we need to do to get the chemical potential of the ideal gas is to take the derivative of this as a constant volume of temperature. So this is what you do. Remember, there is a little bit of a subtlety here because we have the number of particles here, but we also have it right here because n is the density. So it's the number of particles per volume. So please be careful when you derive this, not just derive n, but also derive n right here. And what you obtain when you do it, you obtain this chemical potential, which is a pretty straightforward derivative. And then you find that after things simplify and so on, you find that the chemical potential is nothing else than kBT ln, the n lambda, the thermal wavelengths cube times the density of particle. So this is how you calculate. This is pretty straightforward again by considering all these equations, which I usually find a good place on a crib sheet somewhere. If we remember the result that we find for the Gibbs function, we found the Gibbs function was actually this times n. And what it shows here is that the chemical potential, at least for an ideal gas, is equal to the Gibbs function divided by n. So basically, the chemical potential seems to be the Gibbs function per particle. So you may wonder, well, maybe it's because the ideal gas is so simple. Well, what we are going to see in a few minutes is that this result, that the chemical potential is actually the Gibbs function per particle, is a universal result. So that's going to help us a great deal connecting everything together. Now, in the previous lectures, we've discussed quite a bit about partition function. And the partition function were basically the sum over all possible states, and the sum actually involved the Boltzmann factor. And we were working in what we call the canonical ensemble, and the canonical ensemble is for a system that is in contact with a heat reservoir. Remember that we had a given temperature, that's what the Boltzmann factor came in. So in that perspective, the Boltzmann factor, therefore the partition function, had a temperature as a parameter, okay? But that's all good. But remember, we have not considered that in that time, we have not considered the number of particles. So that's what we are going to do now, that the number of particles can change. So we will generalize actually the definition of partition function, and this is what we are going to do here. So let's try to consider the entropy as a function of U and N. So bear with me here because there are a couple of subtleties. But before we embark in the math, let's try to understand what we're trying to solve. This is very similar to what we discussed when we did the Boltzmann factor. The difference is that I have a system here that has a given energy epsilon and has n particle. And then we have a huge reservoir, as you know, as we discussed before, which has an energy U minus epsilon and a number of particles n rounder minus n. And of course, this number here, n, the n rounder, is very, 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 very large. What it means is that it does not really see a change. It's not affected when particles are moving away from the reservoir. Just the same way as when heat is taken away from the reservoir, the temperature is not changed. That's exactly the definition of reservoir. But here in this ensemble that we're considering, it also applies to the number of particles. So let me repeat this. A reservoir that we've seen before a heat bath was a system for which even if you remove some heat from it or add heat to it, the temperature does not change. And here, the number of particles in the reservoir, and likewise, the number of particles in the reservoir is so large, and when we add to it or remove from it, it makes no change to the system itself. Okay, that's what's important. All right, so we have the entire system, which you consider as a closed system, therefore that has a total energy U and a total number of particles n rounder, like this. And so the question is, what's the probability of this system to exist? Okay, they're just the same way as we did the Boltzmann factor. So let's try to do this. First of all, and this is the most important aspect, is that consider the entropy of this system. And we are going to use Taylor series. Now, the Taylor series, unlike most of the Taylor series you've seen so far, a Taylor series for a two-parameter function, two variable function here. So it's really a gradient, but we just wrote it this way, which means that these two terms are both first order. That's what I'm trying to say. So basically, the entropy for these two variable function is, of course, the one when the two small changes are 0, minus linear corrections coming from this small changes epsilon and n, and of course the derivative are the ones that correspond to the change in the variable. Nothing really surprising, okay? Nothing really surprising. And again, by now you should have a quasi-Pavlovian reflex that those derivative there should be related to something we've seen before, and that is usually where you go back to another slide and find what those derivatives were, and we calculated them. And in fact, if you click on this, you're going to get to slide 352, and 352, we did this calculations. Remember, we did this, and we found those three derivatives. Those three derivatives have been extremely useful for us because they allow us to move forward with the math. So let's try to go back to this slide. And for your convenience, I reminded you the two derivatives from the previous slide that are going to be useful. And so we can directly change those derivatives coming from the Taylor series using those definitions, I would say. So that's nice because we get now that this entropy for this system is the entropy of the system without the change, minus 1 over T epsilon minus mu n. And it comes from just changing the derivative by the definition right here. In fact, to be frank here, there should also be a partial derivative to be completely mathematically correct. But this is fine. So we have this equation here in the green box. Let's try to see if we can go a bit further with it. Okay, so this was the equation in the green box, and let's try to move forward a little bit. So now here's the important thing. The probability of finding a system in a given macrostate, and the macrostate is described by an energy epsilon and number of particle n, is proportional to the number of microstate. So the probability of a state is proportional to the number of microstate. That was a very starting point of everything. Now we know, on the other hand, that the entropy is related to the logarithm of the number of microstate. So we have this kb ln omega. So the entropy is equal to kb ln omega, and that's good because now we are going to be able to connect the probability of a given macrostate with the entropy, which is what we have been trying to do since the beginning. So we've done this, right? Remember, we've done the Boltzmann factor when we didn't have to worry about the number of particles. Now we have to worry about the number of particles, and in fact we have. So we are almost there. So the probability of finding a system with energy epsilon and particle is therefore provided by this. The probability of that state is related to, so probability is corresponding to gamma, therefore omega, probability is proportional to omega, and omega is the exponential of S over kb, right? I just invert this equation. So probability is proportional to the exponential of S over kb, which is exactly what I wrote here. So the probability of finding this is the same, of course, as the probability of finding this, because if I have this, I have this, right? So this is important. The probability of finding this state is the probability of finding this state. Okay. So now that's good because I already have all this. I have just this. And in fact, I can substitute these numbers here, this number, those number here, and of course this is here. This is just a constant that we don't have to worry about. It goes into the proportionality constant. It does not. What I mean in constant, it does not depend on epsilon or n, the straight n, this one. So we can substitute this by this, and since I have a proportionality constant, this term can actually go into the proportionality constant. So in other words, we find a distribution, a probability, which we actually call a Gibbs distribution. So we used a Boltzmann distribution before. Here it's a Gibbs distribution, which actually tells us what's the probability of finding a system at energy epsilon with n particle. And you're going to notice now that if n is a constant, we don't have to worry about it. We can put in the proportionality constant, and we find that the probability of a state of energy epsilon is proportional to e to the minus e to the power minus beta epsilon, which is the Boltzmann factor. So it makes sense, of course, that we obtain back the Boltzmann equation from the Gibbs description, the Boltzmann distribution, sorry, from the Gibbs distribution, if we don't have to worry about the number of particles, since that's what it was built for. So you see that this is what's really important about understanding all this, because we are really generalizing things to do more physics. So of course we call this the grand canonical ensemble. In fact, canonical is usually reserved for temperature, and when we use the word grand, it usually means that we allow the number of particles to change. So before, for the Boltzmann distribution, we had the canonical ensemble, and in this case, for the Gibbs distribution, we have the grand canonical ensemble. So it's worth, and I'm going to write it here, that the probability is proportional to this. And of course, we can make an equal if we normalize the distribution. Remember, that was one of the first things we said in this course, that the distribution is a true distribution if it's normalized. And of course, how do we normalize this? Well, by dividing by the normalization factor, which is nothing else than the sum of all of them. I mean, you can show very easily that the sum of I of pi, but with the definition of z, is equal to 1, okay? And just the same way as we introduced the partition function before, this z here is the grand partition function. So this is, and basically the loop is completed. So we have the whole, everything that we wanted to have here. So that's nice, because now everything that we've done with the partition function can be used for the grand partition function. So remember, just to repeat, the difference between the partition function and the grand partition function is that the grand partition function work for a grand canonical ensemble, where in addition to everything we've learned for the canonical ensemble, we also allow the number of particles to change. That's it. That's not that more complicated. So it's a very good idea to verbalize those things so that it makes them very clear. Okay, now it turns out that just the same way as when we did for that the lecture on the partition function, we can do the same thing for the grand partition function and find various properties, like for example the number of particles. Well, the expectation value for the number of particles is simply a sum of the number of particles for each state times the probability. The energy, the sum of the weighted sum of the energy of each system times the probability. The entropy, we use Gibbs description of the entropy. Remember, we've done all this, where Pi is the probability of a given macro state, just like we did before. And you can do all the math. It's not super complicated. You just have to substitute the pi and derivatives, just like we did in the previous slide. In any case, we can find all those numbers and others, like the Gibbs, like Helmholtz, and so on, as a function of this grand partition function, which is now just the same as what we did before, but the mu and the additional mu n term. Okay, so that's something that's very useful. Again, do not let yourself get into a state of despair because of the number of equations. These are not things that you have to learn by heart, but you have to understand where they come from. And what's most important is other concepts. Okay, so let's try to just summarize where we are with the ensembles. We discussed 3 types of ensembles so far, especially the microcanonical, no, not so much the microcanonical, but we have seen it. The microcanonical ensemble is an ensemble of systems with the same energy. And we knew that the entropy is related to the number of microstates. Okay, so the most likely system is going to be the one that's given by the number of microstates. The one that we spoke a bit more about was the canonical ensemble, and these are ensembles that can that are connected to large heat reservoir, and for that we use the Helmholtz function. And we like to do that because they allowed us to write the Helmholtz function as simply being minus kb t ln z, or more compactly looking at this equation. And finally, we've just seen the grand canonical ensemble, which are systems very similar to canonical ensemble, but they can the system can also exchange particles with a large reservoir. And so clearly we need something. We need to introduce another function to kind of mimic what we've done for the other ensemble. And in fact, that function is related to the grand partition function, really, which is z equal to this term here, just the same way as we had this term here, this omega and z. Well, this grand partition function is going to be related to what's called a grand potential. And I've not spoken about the grand potential yet, because this is what I'm going to talk about now in the next few slides. So let's try to see, to understand a bit the grand potential. So the way we've basically imposed its definition from the previous slide is to write that the grand potential is minus kBT ln z. And we did this in a way that's by comparison with the canonical ensemble, of course. So that allows us to write the entropy. Now, if you go back to the definition of the entropy that we had before, we find that the entropy can be written the following way, and this is what we obtained from all the connection between the grand partition function and the functions of state. So this is what we obtain right here. And now we can try to understand where this term will be coming from. So if I write this, of course, I can rearrange. And then for those of you who remember, maybe, we've actually introduced this term U minus TS. U minus TS was to obtain a function of state where we basically got rid of the TDS and replaced it by SDT. And that's exactly the Helmholtz free energy, if I remember correctly. So indeed, this is here, this is F. So U minus TS is going to be equal to F. And so remember that we wanted this to be the grand potential. So that means that the grand potential really is equal to F minus mu n, okay? So this is coming from the definition of S. Everything seems to work fine. So if we look at the changes in the grand potential, we obtain n minus SDT minus PV minus SD mu coming from the Helmholtz free energy, right? It's minus SDT minus PDV and minus ND mu come here from what we wanted to calculate. Remember as well that the F term included mu dn, okay? But because actually a plus mu dn, and because we subtract mu n, we only end up with this term. So that might be a little confusing, but F already included a term mu dn, and that's how we actually get rid here. So the advantage of this term, of course, now is that we look at changes in chemical potential instead of the changes in number of particles. And so, of course, looking into this, that gives us a number of definitions, again, by comparing these terms with the partial derivative from an exact differential, and we find an expression for S, an expression for P, and also, very useful, an expression for N, which is a number of particles. The number of particles will be minus the derivative of this grand potential as a function of chemical potential at constant temperature and volume. And I do realize this is very abstract. I mean, this is very difficult to imagine or to portray what those terms will be. But bear with me, and the concept will hopefully come clear later. So let's try to keep going with the chemical potential and the Gibbs function. We showed for the example of the ideal gas that the chemical potential was the Gibbs function per particle, right? It was mu was equal to G divided by N. Let's try to see if it's true in general. And if they're extensive, that means they are scaled as a function of the size of the system, right? If the system gets twice as big, the internal energy is twice as big. An intensive variable, in contrast, for example, temperature, if your system twice as big, the temperature would not be twice as big, it would be the same. So internal energy, volume, number of particles, and entropy are all extensive variables, so I can scale them up. So that means that the entropy is scaled. The entropy of the scaled variable is the scaled entropy, right? So this is, if I scale the system, I scale the system by scaling the variable here, or I scale the entropy. So the both, of course, have to be equal. So we can differentiate on both sides with respect to lambda, and then we obtain these equations here, which is very straightforward. And so, of course, from previous results, I'm going to show you what the previous results were, and these are the results that we've already seen used a number of times. The reason why I insist, those results were giving me the derivative of the entropy with the different variable u, v, and n. And so let's try to see here let's go back, okay? So the previous result gave me those derivative, basically, right? So we obtained that derivative, and we obtained this was equal to 1 over t, this one was p over t, and this one was minus mu over t. Remember, it was on the previous slide I just showed you in the red box. Nice, and then we can also suppose that we can actually even make lambda equal to 1 at the end, but the point is, this is true for every lambda, and that gives me a new formulation for the entropy as a function of u, p, v, and mu n. So let's try to see where we can go from there. So I can rewrite this here. Okay, that's very important. U minus Ts plus PV. Remember, we had the internal energy, and we wanted to get rid of the TdS and the PdV, and we added those two terms. And if you remember well, we did this to get a new function, which was the Gibbs free energy. So the Gibbs energy, G. So this is actually G. So actually, G is equal to mu n. So we can show in all generality that the chemical potential mu is G over n. I'd like to attract your attention on an important point here. Physicists and chemists defined Gibbs slightly differently in terms of on a per mole versus a per particle. So physicists tend to prefer a per particle description, while chemists use a per mole. So be careful when you compare this to chemical results. Sometimes the n becomes a number of moles, and then this is where you have different formulation where physicists very often use Kb, and in chemistry you have R, the constant of gas, but of course the difference between them is the number of particles in a mole. So just like to attract your attention on this, this is not going to be a focus of this course, but it's also important to be aware of the existence of this possible difficulty. Okay, so the result that's important, it probably deserves a title on its own, is the chemical potential is the Gibbs energy divided by the number of particles. So if you go back in the previous slide, and I'm not even expecting people to remember this, we find that the grand potential was the Helmholtz function minus mu n. We also know that F is U minus Ts, and we know that G is U minus Ts plus PV. Those two we've seen many times before. And that allows me to write, if you subtract everything that you need to subtract here, and of course F minus mu n is going to come, U minus Ts minus mu n, so that's almost the same as G, but G is mu n, so it's F minus G. F minus G is U minus Ts minus U minus Ts plus PV. So what we have left is minus PV. So the grand potential is actually minus PV. This is what we find. That's coming a little bit of a surprise, maybe to many, but this is the expression of the grand potential. Okay. Imagine now that we try to do this in a little bit more general way, and we have more than one particle, because so far we have one type of particle that was described by a simple chemical potential. But imagine that you have more than one particle and more than one chemical potential. The extension is fairly straightforward. The extension is simply by adding more terms to the internal energy. And so, of course, everything that we've defined so far, like the Helmholtz function or the Gibbs function, we can also all inherit this change in U, because, as you remember, F and G are defined originally as a function of U. And finally, we find that the Gibbs function, the change in Gibbs function, is actually related to the change in the number of particles for each type. So this is what we get. So the change in Gibbs function is obtained by looking at all the changes in the number of particles for all the different type of particle we're considering, multiplied by the chemical potential. Of course, this is particularly important for chemical reactions, but it's also important for other type of problem. Now, we've done quite a bit already, but the best is still to come. And let's try to think about how we connect, how we understand better the chemical potential and number of particles. So we are going to look at the number of particles and the conservation law, okay? So imagine that we have a system at constant volume and constant temperature, and that system can change the number of particles. So the number of particles is not a constant of the system, okay? So in that case, if I work at constant volume and constant temperature, you just look at your list. It's if it's constant volume, you already know that it removes enthalpy and Gibbs. But if it's constant temperature, it removes internal energy, since it's described with a constraint of the entropy. So the only ones left, it's the Helmholtz. So the function, the appropriate function for a system at constant volume, constant temperature is Helmholtz. That's what we do. We look at the change in Helmholtz function, and then we can, which is of course the definition that we started from, and we end up with this expression for the Helmholtz of energy. We've already done this before. I'm just repeating it here, just so it's simple. Okay, so good. So of course we know that due to the second law of thermodynamics, this is going to be minimized. As opposed to maximize, of course, because maximizing ds is going to minimizing f, obviously, because of the minus sign. Okay, so we want to minimize f. That means that we want to minimize f as a function of the number of particles. So that's what we want to do. Okay, so let's try to see how we do this. And here I apologize, but this equation is the generalized equation for many types of particle, while this equation here is just for one particle, but you can replace the sum here. That's the same difference. Okay, so let's try to focus on this one with one type of particle. We want the derivative of f. We want this at equilibrium. At equilibrium, we want all these things to be zero. We don't want the function to change anymore. It's in equilibrium. And so this term, of course, is mu, according to this equation, right? At constant volume and temperature, this is going to be mu. And that means that at equilibrium, the chemical potential will be equal to zero. So in other words, if you do not impose the number of particles to be constant, or if there is no constraint on the number of particles, the system is going to change until it's going to change the number of particles. Okay, not just exchange particle, but change the number of particles until the chemical potential is zero. So this is important because, and we are going to see that especially for photons, that this result shows that if we let the number of particles change at will, the chemical potential is zero at equilibrium. I mean, this is not going to be the case if we actually lose particle all of the time. We actually are going to see an example now of a system where the number of particles is actually imposed. We just cannot lose particle like this. But if we have photons, for example, and we'll study that in a couple of lectures, we'll see that this is important, that in that case, the system will evolve such that the chemical potential is zero. Let's try to have an example of this where the total number of particles is conserved, and that will apply to electrons, for example. So let's try to consider that we have the annihilation of an electron with an anti-electron or a positron, and that creates a photon. So that's something that's a well-known possible reaction between an electron and its antiparticle to give a photon. And so this particular case is going to create is going to start from two particles, and you know that the number of particles there is a constraint on the number of particles. So let's try to consider a box where there are n minus electrons and n plus positrons. And we're going to the conservation law. So here the conservation law is not so much about the total number of particles, it's the fact that each time there is an electron that disappears, also a positron disappears. In other words, n minus minus n plus, so the net difference between the number of electrons and positrons is going to be constant. That's the idea. So you can add electron so long as you add as many positrons, and you can remove electrons so long as you remove as many positrons. So that means that because it's a conserved quantity, we know that it leads to the fact that at a constant n, the change in the derivative of the Helmholtz function with respect to the number of electrons is going to be equal to 0 at equilibrium. So what we need to do now is to minimize the problem, to again minimize the Helmholtz function, but with the additional constraint on the number n. So that's what's very important here. So we have added a constraint. So on the previous slide, that was a different story, because on the previous slide we did not put a constraint on the total number of particles, and that led us to find that at equilibrium, for such a system where the number of particles is not fixed or constrained, we find that the chemical potential to be 0 at equilibrium. This is different here because we have an additional constraint. So let's try to have a look at that. So we can write this here by calculating the total change in the Helmholtz function f with respect to the change in the number of electrons and number of positrons. Okay, so we know we already rearranged the dn plus and the dn minus here, but the point remains that this has to be equal to 0 at equilibrium, and you can see that as a total change, as we've used that kind of equations very often. So of course we also remember from what we've done before that the change in Helmholtz free energy with respect to a number of particles is the chemical potential of that particle. That was one of the key results that we found, and we can apply this both to the electrons and to the positron. At the same time, the change in electron and the change in positron has to be the same. So each time I gain an electron, I have to gain a positron. Each time I lose an electron, I lose a positron. This is coming from this equation. So this ratio here has to be equal to 1. Remember, this is what we impose. What we impose is n minus minus n plus to be a constant. Okay, that's important. Now we can change, we can introduce all that in here, and what we find, of course, is that at equilibrium, the chemical potential of the positron plus the chemical potential of the electron has to be equal to 0. Okay, so one thing that you can ask is, oh, why don't we have to worry about the chemical potential of the photons? Well, for the reason I just gave you on the previous study that shows that, in fact, the number of photons is not conserved in general, and so that we can actually pick the chemical potential of the photon as being equal to 0 here. So there is no conservation law for the photon. So that's very good. So now let's keep moving, and so we see that depending on the constraint and the number of particles, we get a different result, which is fine. Of course, it's a minimization problem under different constraints, and of course we get different results for that. Now, let's go and focus on the coming slides, and it's probably on the next dozen or so slides. Let's focus on the chemical reaction, and the question we want to ask is, what's the equilibrium position of a chemical reaction, taking into account the fact not just the energy as we've seen before, but also the number of particles. Remember that we do have some principles that are linked to the number of particles, and the principles related to the second law of thermodynamics, which is related, of course, to the maximization of the entropy. And as we've seen before, the number of particles, there is going to be a change in a number of particles to maximize the entropy. And that change, of course, will also depend on the constraint that we have. So let's try to formalize all this. So let's try to think a little bit about the chemical potential of an ideal gas. And of course, we already know what the chemical potential of an ideal gas is. It's something we calculated in one of the previous lectures. And then when we found that the chemical potential is related to the logarithm of the density of the gas times the thermal wavelength to the power 3. So the first thing we need to do here is that we would like to bring out the pressure from this equation. In fact, the pressure is hidden in the density n through the law of ideal gas. In fact, I reminded you here it's P equal NKBT. You may be more familiar with PV equal to capital N KBT, but of course, capital N divided by V is a density, which is lowercase n. So in any case, you can get from the first line to the second line pretty simply by noting that P is equal to N KBT, and you actually can work your way backward to see that these two equations are the same. And again, the goal of this is to bring out the pressure explicitly and to make our life easier, because a lot of things that we are going to discuss now will be in terms of pressure. So what chemists usually do is define a set of standard temperature and pressure. And they do this by introducing a notation which is with this symbol as a superscript on P, T, and mu. And the pressure is 10 to the power 5 Pascal, which is 1 bar, and temperature is 298 K, which is the room temperature. And you can calculate the chemical potential, the standard chemical potential, the standard pressure and temperature, and also using the same notation. So these are notations that are very useful, and it actually allows to compactify a little bit the notations later. And if you calculate mu standard using the equation, the second equation on this slide, and you can actually see that in general mu can be written the way it's written on at the bottom of this slide here. I invite you to do this little exercise. It's not that complicated. It just comes from the fact that the logarithm of a ratio is the difference between the logarithms, and that allows you to have a more compact description. And then you will notice also that the reason why we do this is that we did this at the beginning to separate the equation was to really be able to write the pressure and temperature explicitly. So one thing I'd like to say is this equation is the physics version of the equation where we work on the chemical potential per particle, so per atom, per molecule, per entity, if you will. Chemists usually prefer to work in mole, and so they will actually use the chemical potential per mole, simply because these are more macroscopic properties that are measured in the lab. And as you know, I mean, you can just mu and mu standard are going to be defined as per mole instead of per particle. And of course, when you divide by the number, the Avogadro number, when you divide Kb by the Avogadro number, you get the constant of gas, R. So a very good rule of thumb when you do look at equations like this, if you have an RT, it's usually a per mole. It's usually what chemists do. If you have a KBT, it's usually per particle, and this is what physicists do. So the equation look the same. Of course, there is a factor 10 to the power 23 between the values. Usually you can tell which one is which one just by looking at the units. But this is something to remember. This course, of course, is not a chemistry course, and it's not the point is not so much to try to understand what every community or what all communities do, but this is also a good idea to make sure that we know what we are doing. Okay, so now let's try to go back to what we are trying to do. And what we're trying to do is to understand this equation. This is a chemical reaction. And of course, this chemical reaction has two arrows. We've seen this in chemistry, a forward arrow and a backward arrow. The idea is that those arrows say that there is a way to transform the product A into the reactant A into the product B, but the other way is possible too. And the question we ask ourselves is, how do we get to equilibrium? Okay. So let me try and introduce you a notion that you may have forgotten from basic chemistry. We are talking about the partial pressures of A and B. that we know PA and PB. So let me try to define the partial pressure PA and PB, which is, and the partial pressure is the partial of a component is all of the other components vanished. In other words, imagine that there is only A in a container, and then you look at the pressure of A and B. Even though they are together, the partial pressure is like this. And of course, the sum of the partial pressures will be the total pressure. Now, we define the equilibrium constant, K, as being PB minus divided by PA. In other words, if PB is much larger than PA, okay? So if K is much larger than 1, that means that this equation leans to the right. They are mostly B. So in other words, this reaction is going to go forward a lot. Now, if PB is much smaller than PA, K will be much smaller than 1, and that means it goes to the other direction. And of course, if K is equal to 1, you have as much pressure of A and pressure of B. So just to remind here, if K is very small, that means that PA is much larger than PB, and the reaction goes to the left, backwards, mostly A. Okay, so let's try to see here what we have in the change of the Gibbs function. If you remember a few slides ago, and this is the slide where I introduced you the cases where I have more than one type of particle, this is what we have to use, and we find that the variation in the Gibbs function at constant pressure and temperature was actually obtained by mu, was actually a sum of I, mu I, d and I, if you remember. So in other words, the total change in Gibbs function is the change due to one particle and the change to the number of one particle and the number of the other particle. So, of course, we know in this particular case, there is no particle that disappears. I mean, there are some that transform, like Lavoisier would say. So the number of particle, if each time you lose a particle of type A, you gain a particle of type B and vice versa. So in other words, D and A is equal to minus D and B. That's the reason why we can write this here. So this is the Gibbs function here. All right. So of course, we also understand that we are still working here, and this is what the asterisks are, to be careful about talking about chemical potential as a function of particle rather than number of mole as chemists do. But I think that I made that point pretty clear so far. So the molar Gibbs function, which is what chemists do, is per mole, is going to be, these are going to be given with R. We discussed this already, and we know that those delta G are going to be related to those changes as well. So let's try to study. So let me go back to this slide a bit for a couple more seconds, just to make the connection between the two. So we know that this dG is going to be related to the partial pressure of A and B, and this is what we study. So if we look at the previous section that we had, we still have this, and we also have that K is equal to PB divided by PA. And we know from the previous section that we want to understand what's going to happen to the reaction. So first of all, we know that the principle for the second law of thermodynamics, and I again invite you to go back into the lecture on thermodynamic potential and the availability function that we introduced, will always happen in such a way that G is minimized under the condition of constant pressure and temperature. Okay, so it's going to be minimized. So in other words, a negative delta G will be what nature will choose to do, and because this is going to be the one that maximizes entropy. So basically, if delta G is negative, all right. So if this number is negative, that means that if it's negative, that means that the direct product occurs spontaneously. So that's what it means. If it's negative, that means it's the normal process. So it's A is going to happen A to B. If it's positive, that means that it's not. It doesn't like this. It doesn't like to do this because delta G has to be minimized. But here, if the change is positive, that can't be. So that means that you have to change the direction of the reaction. And of course, at equilibrium, the delta G has to be equal to 0. In other words, you have reached a minimum, and any variation in G will be equal to 0 around the minimum. I mean, that's the derivative will be 0. And that's an equilibrium. And in that case, this term here is equal to 0. That means, in other words, that I can say, I can actually replace PB over PA by K, the constant, the rate constant. And you find, of course, that ln K is equal to minus delta G over RT. Okay, so these are all things that we discuss into a per mole basis. So the equilibrium constant, the reaction constant, is simply given by the change in the Gibbs function for standard at standard condition divided by RT. So that's nice. That's a result that you have seen in your chemistry course, and that we could understand it fairly straightforwardly here in thermodynamics. Now let's try to generalize this, because we had just one particle transforming into another particle, A goes to B. What happens is I have a number of reactants on the left that I'm going to have use the label J for them, and a number of products on the right that I'm going to also product J, but they're going to go from P plus 1 plus 2 P plus Q. So basically they are Q products and they are P reactant. And so we are going to try to understand this. In order for things to be easier later, we are going to suppose that the coefficients here on the left are negative. We will see how that works out. But that way, when they have a negative coefficient, that means it's a reactant. That will allow us to be a little bit more general. The best way is to show you an example. Let's suppose that you have this reaction here. So it's the creation of ammonia from hydrogen and nitrogen. What you find in this case is, of course, we have one product, and the coefficient is 2. That's what we find here. So mu3 equal 3, mu3 equal 2. And then we have two reactants, okay? Two reactants on the left. And of course, we have a negative number because they are reactants. This is the negative number here. So -1 and -3, okay? So that's going to help us. This is just a notation, if you will. There's not much to understand on this. This is something that's going to come very handy as we move forward. So we know at equilibrium, if you remember, the Gibbs function is simply the sum of mu J, D and J, right? So you take all the particle, and this is why the sum goes from 1 to P plus Q, so all product and reactant. You know that at equilibrium, the Gibbs function delta G is equal to 0, but delta G is this, right? This is this at constant pressure and temperature. So that's nice. So this is an important result. And that means now that at the same time, if you remember how we've worked things out, we can write this. And just let's take a second for you to understand how we go from here to here. It doesn't seem so obvious, but it's actually not too complicated. Mu J, fine, it's the same on both sides. There's nothing to understand. Now, remember that we have a chemical reaction, and this D and J is how many particles you change of type J, either a reactant or a product. However, my reactions use integer numbers, right? So we have integer number of particles, but even if we did not, each time we change one, all the others are changed by the same factor. So in other words, the D and J are all proportional to this new J, right? Because this is due to stoichiometry of the reaction, all right? And so this is where we see that it was a good idea to define negative nu J for the reactant and positive nu J for the product, because D and J is going to be negative, for example, for a reactant, if it's a forward experiment, forward reaction, it's going to be positive for the product, for a forward reaction, and vice versa, of course. Since it's equal to 0, it's fine. So now we have encapsulated, we have considered everything in this equation, okay? And nu J, remember, this is the coefficient that come from the chemical reaction. So let's try to see the same example with ammonia I mentioned before, so we understand this. And now what happens is that at equilibrium, minus mu of this, minus 3 mu of this, plus 2 mu of this is equal to 0. And this is exactly saying, this is exactly an example of this equation. And what's happening with this is that it is due to the fact that the Gibbs function should be minimized. In other words, any changes dg should be equal to 0. And this is exactly how we write it for a specific case of a chemical reaction. Okay, so that's nice. So now let's keep working. Now, we can also come up with the equilibrium constant. The equilibrium constant that I explained for the A to B reaction, where just PA over PB is equal to K, right? And that we actually, it's just PB over PA, because we put the product on the top. We put the product on the top. All right, because this is the equilibrium constant for the forward reaction. In other words, K will be larger than 1 when it's going forward and smaller than 1 when it's going backward. Okay, now this description here, and of course you recognize the product term here, simply means that we are multiplying all those products here with the proper exponent. So once again, we are lucky that we have defined nu as being positive or negative. That way, all the reactant will actually show up at the denominator because it's a negative, and all the product at the numerator. And we always calculate this as a ratio between the actual pressure, the partial pressure of that product, divided by the standard pressure. Remember what we discussed, standard pressure, which is the atmospheric pressure. And so this exponent is different depending on the balance of the stoichiometric reaction. So this is not a very complicated equations, but as so long as you can dissect it and just the way I did it. So let's keep building our example here. And of course, if we apply this, this formulation for the equilibrium constant of this reaction, we end up with this here, where we have a factor 2 that comes from this one, a factor minus 3, so the denominator coming from this one. So sorry, from factor power 3 that coming from this one, and a minus 1 coming from this one. And of course, the result for the equilibrium constant is that you see that we have a square of the partial pressure, the standard partial pressure, and it's pretty easy to understand why we need this. Is because you need, of course, K would be unitless. So you have pressure to the power 4 in the numerator, pressure to the power 4 in the denominator, and that's it. And that way it's unitless. Nice. Let's keep going with all this. So we have this definition of the constant, the reaction constant, and that completely justify why we have to use nu here or instead of just the sign. Let's try to see that how it works. Let's see why this works well. Now we have this result that's basically an embodiment of Gibbs function that has to be minimized. Let's see how we can go from this. Now we know that the mu, the chemical potential, has been described a few slides ago as it can be described as a function of the pressure, okay, and temperature. And we could write this as a function of the standard chemical potential. So we just substitute this. Then, of course, we can come up with, we can remember what is the molar, what the R here, the subscript R means it's per mole. So the molar Gibbs change in Gibbs function, the standard one is just obtained by using the standard chemical potential. That's actually a fairly straightforward definition. That allows me to simplify this a bit, that replace this term by this term. So I end up with this term plus whatever is left on the other side right here. That's going to be equal to 0 at equilibrium. So this equation is just this equation here with a little bit of where we replaced the chemical potential. Now, why do we do this? Well, we do this because just take a second to think a little bit about the math. Here we have a sum of nu j ln pj over p phi. Well, clearly, if it's nu j is in the front, you could probably put you can definitely put nu j inside the logarithm as an exponent, right? No problem. But the sum of a logarithm, okay, is the logarithm of the product, right? The sum of a logarithm is the logarithm of the product by definition. So probably you see something that starts to look a lot like this, right? So in other words, it's like this. This term here is nothing else than logarithm of k. If you're not convinced, just work it out backward. The logarithm of a product is the sum of the logarithm, and the logarithm of this can take nu j outside like this. So this justifies a posteriori why we needed this exponent nu j. Okay? All right, nice. So this is very important because this is what's happening at equilibrium. So at equilibrium, we have this, and of course, that's an extremely important result, that the logarithm of the reaction constant here is minus delta G at standard G divided by RT. So we've done this, calculated this before, but here it's generalized for any reaction regardless of the stoichiometry. So it's just not A to B, it's any reaction. That's very nice. So K is going to tell you basically what's this property here. What is the relative pressure, partial pressure of each reactant and product. So very powerful. Let's go one more step. So we found this on the previous slide. Okay. Now we can also take the derivative of this with respect to temperature. There is nothing that stops us to do this. And this is where students hate thermodynamics because they do sometimes remember that they've seen this before. What is delta G over T? They do remember it, but they don't know what it is. They just remember something happened. Well, it turns out if you use the Gibbs-Helmholtz relation, and actually I have a link here, so I'm going to bring you and look at the slide number. So bring you all the way to this slide where we were able to show the Gibbs-Helmholtz equation that were that the derivative of G over T was equal to minus H over T squared. So that's what we found right here. So using the Gibbs-Helmholtz relation tells me that the derivative of delta G over T is minus T squared H, H being the enthalpy. So minus H over T squared, yeah. So that means that we obtain this equation that's very important, that the derivative of ln k with respect to temperature give me essentially the enthalpy, which, as you know, the enthalpy is at constant pressure, it's actually the heat of the reaction. All right. So if we have an exothermic reaction, so delta H negative means that heat comes out of the system, so it's exothermic. That means that if it's negative, that means that the logarithm of the constant goes down, right? The derivative goes down, so k goes down as t increases. So if when t increases, for an exothermic reaction, if we decrease the temperature, we have fewer products. So it's less, is going less to the right because k goes down. Okay, k goes down. On the other hand, if we have endothermic, so positive means we get heat into the system, just using the convention we've used since the beginning. If the temperature increases, then you increase the reaction constant. In other words, you have more product, so it goes more to the right. And if you remember probably your high school chemistry or your introductory chemistry, this is just an example of the Le Chatelier principle, which means that a system at equilibrium, when subjected to a disturbance, will respond in such a way as to minimize that disturbance. The idea in this case is that if for example, let's have a look at the exothermic case, and you can apply it to the endothermic case. if we have an exothermic system, you would expect that the surrounding temperature will increase because heat is released to the surrounding. Now, if you decide to increase it yourself, the system will actually respond to minimize the disturbance. So that means that to make it less negative, so in other words, to not favor that reaction. So that's the idea, and you can apply the same in this case, in the other case. So this is Le Chatelier principle. Okay, one more thing that we need to do is to look at the Van 't Hoff equation. So this is the equation we found on the previous slide. And remember, we needed to use the Helmholtz-Gibbs equation to find the derivative of delta G over T. That's how we did the connection. Now, we can make a small change here. And instead of doing the derivative of K with respect to T, we can actually calculate the derivative of ln of K with respect to 1 over T. This is just a mathematical manipulation. There is nothing really crazy about it. The advantage is that by doing this, you actually get rid of the 1 over T squared, the minus 1 over T squared on the right-hand side. So the right-hand side is just the heat minus the heat of the reaction as in standard conditions divided by the constant of gas. So that's nice. It's just one number. Okay. So this is the Van 't Hoff equation, and this is a good equation to use in practice, because if you measure, if you actually plot ln K with respect to 1 over T, you can find the slope of that function is going to give you the heat of the reaction. So for example, here, if I plot ln K as function of 1 over T, you get a slope. In this case, the slope is positive. That means that delta H, the standard delta H is negative. In other words, this is an exothermic reaction right here. So for an exothermic reaction, you are going to see things going this way. So this example that I plotted here is for an exothermic reaction. And I'd like to show you one more example before we conclude this part on the chemical reaction and we move to osmosis, is the example of molecular hydrogen dissociation. So you have a hydrogen molecule and you get two protons, basically. You know, first and foremost from your chemistry, that this is not a favorable reaction. I mean, hydrogen does not just not spontaneously decompose into protons in standard conditions. All right, so we probably expect this equation to be endothermic, so need heat to happen, and we also expect the reaction to be strongly to the left. In other words, that K should be very much smaller than 1. Let's see what happens. And we have here experimental data that have been obtained from the Blundell and Blunder's book. And first of all, you see that if you look at the reaction constant K, it's indeed very small. In fact, it's tiny, extremely small, right? 10 to the minus 35 even at 500 Kelvin. It's just saying that this reaction basically does not have any partial pressure of the positrons, of the protons compared to the hydrogen molecule, and it's normal because you need to actually provide heat in the system to happen. So what heat? Well, actually the property is here by using Van 't Hoff equation. If we plot the logarithm of K with respect to 1 over T, you see that there is a line, almost straight line, and it's actually the slope is negative. But remember, the slope is minus delta H over R. So the fact that the slope is negative means that delta H is positive, and we find here the slope is about 440 kilojoule per mole. This is the heat that's needed. It's a positive number, so it's heat that's needed to the system for the reaction to happen. So these are things that happen a lot in chemistry. Okay, it's now time to move to the final topic of this lecture today, which is a very rich lecture with a lot of new concepts, and so that's probably one that takes a little bit more time to digest. But I'm going to try to explain this in detail for you. Entropic force. This is a very fascinating subject, And I'm going to show that to you now and show it to you for one example, and I will also mention one other example. But before we talk about force, let's try to remember what we've done since the beginning of this course, before we spoke even about the number of particles. We knew from the second law of thermodynamics that if temperature T1 is larger than T2, and if we impose the work that no work can be done, then we see that the heat, in that case, the heat is going to flow from the hot reservoir to the cold reservoir, right? Or to the cold system to the hot system. And so it's going to do that until the two temperatures are the same. So it does not really apply to reservoir, because the reservoir, we suppose temperature are constant, but say two subsystems. So it's going to do that. So heat is going to keep flowing from the hot to the cold until the entropy is maximized. So that's fine. Okay, we understand that. So it almost looks like there's a force. We don't have to talk force because there's no particle involved here. But there's kind of a driving force, should I say, for heat to move this way. And remember, we discussed that there is a parallel between temperature and chemical potential. And I'm trying to draw the potential, the parallel here. And imagine the two temperatures here are the same. These are plots I already showed to you, so this is just a reminder, just to make sure that it's clear. The point is, there will be particle leaving subsystem 1 to subsystem 2 if the chemical potential mu1 is larger than chemical potential mu2. That's just a fact. We just come from this, from the entropy. So due to the entropy being maximized, there will be particle moving away from the high chemical potential system to the low chemical potential system. So for all practical purposes, those particles, could be electron, could be molecule, can be gas, whatever, will actually move this way. There will be a net flux of particle going this way. So it will really look like there is indeed a force moving this particle from here to here. And because the origin of that force is purely entropic, the idea would be to maximize entropy. We call that an entropic force. So you may say, well, that's nice. Entropic force looks like a very fancy subject that we probably does not have much practical application. So what's up? Well, it turns out that entropic force is essentially one of the reasons why the living cells are actually alive. Let me explain to you first about this. So as exactly as I just said, to maximize the entropy, I just explained this without the words, but these are the words on the slide. Okay, an example is osmosis. So osmosis goes like this. Imagine that you have a large container with a pure solution A. Then you take a small container which has a solution of A and B. And the B molecule are in much smaller amount than A, for example. They're in this container, and this container has something special at the bottom. It has a semi-permeable membrane. And a semi-permeable membrane is a membrane that lets some molecule, the small ones, going through, and the large ones cannot. So this membrane here is done in such a way that molecules A can move back and forth through the membrane, but molecules B are stuck above the membrane. Okay, so this is something this is a starting point. So the question is, what's happening if you have such a system? What should happen? Okay, so before we go into any math, let's try to understand a little bit what we expect to happen. We know that any system is going to move towards the maximum entropy. What's an entropy? Maximum entropy is a system that has the largest number of microstates. So we have a pure solution A, and we have a dilute solution of B into A. So clearly, in order to increase the number of microstates, we would like to dilute more and more the A plus B solution. I mean, if you're not convinced by what I say, it's going to become clear when we work out the equation. So in other words, you do expect A to try to go into the A plus B solution, right? Or you can say, well, unless in order to increase the number of microstates, B should go into the pure solution A. In either case, you are trying to get to maximize the number of microstates. The problem is that the second possibility I gave you to get B through to the membrane is not possible because the semi-permeable membrane is such that B cannot go through that semi-permeable membrane. So the only possibility is for molecule A to go through the semi-permeable membrane, and this is due to an entropic force. And in fact, when you do that, what you find because of this, that indeed some molecules A go through the semi-permeable membrane, and there is an increase in the height of the liquid at equilibrium. And this is due to an osmotic flow. And the reason why that column stops there is because there is an osmotic pressure pi, and we will spend quite a bit of time calculating it, which is just the usual pressure that we know, right? That we've seen, rho gh, with rho being the density of the solution, and it's basically the pressure that we have to apply from the top to stop the rise of the column of the solution. So basically, the osmotic pressure, it looks like it's raising the solution because A plus B, because of this osmotic force. So this is something that's fascinating, because there is a force that's simply due to the fact that the system is trying to maximize the entropy, and this is osmosis. So osmosis, and what I'm going to do now, I'm going to show you a couple of examples in real life, and then we will analyze this quantitatively. So importance of osmosis. Consider a plant. A plant is made up of cells, and what you want is the cells to be able to absorb water with nutrient, and then you know also that the plant is, there is evaporation, there is transpiration of the plant. So it turns out that you can say that the particle sucks up water with nutrient, but this is not. There is no sucking up. It's actually related to the osmotic pressure. In fact, we can represent this system as the outside water as being the solution A, and the plant itself being the solution A plus B, and that makes the system behaves like there is absorption of the water from the roots through the osmotic pressure. So, and it provides an internal pressure, which is similar to the pressure I just mentioned to you, the capital letter pi. For plants, this is called the Turgor pressure. And it does actually provide the structural stability of many plants. Indeed, it increases the pressure within the cell, which avoids the cell to collapse. So in other words, the cell can keep functioning because there is a pressure that's due to the osmosis with the outside. So this is very important. The water in the ground raises up the roots because of this osmotic pressure, because of the difference between the density of ion between the outside and the inside. So this is important. And why the sucking up keeps happening is because of the transpiration. Water evaporates from the leaves, and also, in addition to cooling, it also basically releases the pressure, and then that means that there is more sucking up. Just imagine that the top schematics that I have here, if we removed more and more here from evaporation without removing, it would keep pumping up. That's not a pump, of course, but it would keep going up just to keep this pressure that we discussed before. That's nice. And of course, that means that you have to water your plant, otherwise you will see that the plant is going to wilt, and the wilting basically means that you are essentially removing the pressure inside the cells, and there's a reason why they collapse. So if you try to water your plant with salty water, you have the same effect, because now the salty water, what happens is that the plants try to the water in the cell, so in the plant, has less water, so that has less salt. So what it's trying to do is to add water to the salty water outside, and then of course what happens in that is that you also have an osmotic flow, but outside, because the salt cannot get inside. So these are methods that have been used also to as a to, to to get rid of slugs and stuff like that. But I think that there may be maybe other ways to do that. Let's not go there. Instead, let's have a look at another effect, osmosis in fish. The question you can ask yourself: why are there freshwater fish and saltwater fish? And usually, I mean, uh, fish a freshwater fish cannot live in salt water and vice versa. And the reason for this is because the osmotic pressure is different in both cases. In one, a fish lives in a salty water. The other one is it lives in a water that is essentially no salt. This is the fresh water. So the fish have to find a way to regulate this and to make sure that the pressure can be there, and I mean it can be maintained in the cells. Uh, that's the reason why there will be different organs that are used for the different fish. For example, a fish in salt water, like it's written, like it's shown here, will have a way to 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 get rid of ions, for example, because just to maintain this osmotic pressure between the in and out. So in fact, this is the osmosis is related to this and to the change in concentration between what's in the cell of the animal and what's in the environment in the which is in this case the water, okay, salty or not. So some system like the amoeba has actually can live in both conditions, but there is a way to discharge the water um, from the system to avoid issues with this. Actually, there is another example which is even in human beings. It's related to the blood cells. So when you have a blood cell, so they carry for example they mostly water in there. So if you do a transfusion um, of blood, you want to make sure that the cell will have isotonic. Isotonic means that they have the same uh, osmotic pressure. In other words, if they have the same osmotic pressure, there will be no excessive exchange or too small exchange of of water between the cells and the blood itself. So what it means is that if you have an hypertonic system, uh, if the blood is too concentrated, okay, so in that case, you have a transfer of water from the cell into the blood, into the blood that you just transfuse, and that means that the cell, the red cell, actually collapsing in this case. It could be the hypertonic, so it's too high osmotic pressure uh, uh, in the system in the blood cells. So you can also have a hypotonic. In that case, the cell can burst because there is a lower osmotic pressure than blood, and therefore that means that there is a water coming from the stream into the cell itself, and it's called the hypotonic. So hypo, it's lower, too low pressure inside the cell, and here too high pressure inside the cell. So what you want is the isotonic. So you want the the blood that's injected has the same osmotic pressure as the cell themselves. Therefore, the the net amount of water coming in and out is the same. So you have a stable system that's neither collapsed nor burst. So it's pretty serious. Uh, Now we can go back and try to understand a little bit the mathematics behind osmotic pressure. Remember that the osmotic pressure is a purely entropic effect that's try to essentially uh, the, change the solution here. So from a pure solvent, so bring solvent molecule from the left to the right to dilute this more and more to try to have the same composition on both sides. Of course, cannot do that because of the semi-impermeable membrane that does not allow the B molecule that are in this solution to move to the left. So that's the reason why there is this effect. So after, this is the initial case, but after at equilibrium, there is a pressure that's maintained here, pi, that's the additional pressure compared to, let's say, the atmospheric pressure, P, that is maintained, so that you actually have an equilibrium between the, the flow of the osmotic flow and the pressure that result from it. There is another thing that's used a lot, in fact, in filtration and desalination. So that in this case, what we want to do is not the solution to go into this. It's not pure solvent to go into solution, but instead getting rid of things that are in the solution. For example, we want the pure solvent that is a solution to move to the left. Okay, so it's called reverse osmosis. So we want the solution to be more and more concentrated here, and only the solvent to go to the left. This is called the reverse osmosis. And how do you do that? Well, you know that the direct osmosis will lead to the transfer of molecule of solvent to the right, and it will lead to a pressure. Okay. Now, if you apply a pressure here that's larger than the osmotic pressure pi, that means basically you are reverting the system, you're reverting the problem. So you are basically, so long as your pressure is at least the osmotic pressure, but it should be a bit more, then you will start to reverse the systems, just so that you are in equilibrium. It's called reverse osmosis. And it's actually a very important effect that that's used in desalination and filtration processes, and it's more and more important, especially now that we need fresh water, getting rid of the salt. So this is actually, I have an example here from some work that I've done in the past with some of my colleagues, and this is an example of a molecular dynamics simulation, and the goal here was to have here the solution A plus B with ions. You see that in green and blue, and water, right? And so the research here is to work in nanoscience to try to develop those semi-permeable membrane. And the idea is it's not so hard to do a membrane that filters, but what you need to do is to also do a membrane that let the water go through fast. So the water here is the solvent. So this is an example of what's happening. And you can see it here that all the water goes through, and while all the ions stay on the top. This is something that works well. And the piston here is essentially that pushes it. So all the ions are here. And this piston, so long as the pressure imposed by this piston is at least the osmotic pressure, these things work. And we have strapped all the ions on the top, and you have pure water on the right-hand side. So this is work on desalination, and this is essentially the development of a new nanostructured semi-permeable membrane for this application. Another example of entropic force, in addition to osmosis, is of course due to a rubber band. Remember that the rubber band was a special rod when we looked into that lecture on rod bubbles and magnetic moment. Basically, if you look at a molecule, a long polymer that makes up rubber, you see that when it stretches this long molecule, you actually decrease the entropy, and this is because you have a single long molecule. And the decrease in entropy comes simply from the fact that the number of configurations of a straight structure like this is way smaller than the number of configurations when they make this aggregate. So that means that if you have fewer microstates, you have a decreased entropy. So that was special to rubber, as you remember. Now imagine that you extend rubber like this, and you put a weight in the bottom, and you start to heat it. So if you heat it, you are essentially increasing the entropy. And so increasing the entropy means that you are going to move here. So this increase in entropy, which correspond to entropic force, will actually lift the mass that you put at the bottom of the rubber band. So basically, if you put a mass at the bottom of rubber band and you heat up the rubber band, you will see that the mass will go up. And this force is actually entropic in nature. It will not work if you do that with a metallic rod. If you use a metallic rod and you heat up the system, it's actually going to go down. That's what's going to happen because the rod increases its entropy, by pulling on it, a metallic rod, but not rubber. So rubber will actually lift the weight against the gravitational field, and this is an example of entropic force. Okay, so we need to do one more thing in this long screencast, and that thing is to be able to calculate this osmotic pressure. So before we can do that, we are going to calculate the changes in chemical potential of the solvent A with the solute B, okay? So remember here, it's a definition, the mole fraction of A is the number of moles of A over total number of moles of the system, okay? So that's one thing that's going to happen. We will note, the notation for this will be X with the subscript B, A. So first of all, remember that for the gas, we saw this. We spent quite a bit of time writing the chemical potential of the gas for A as a function of the standard properties, which is pressure and temperature. And then here we introduce a new notation, which is an asterisk, which simply means that it's a pure substance. So we have a pure substance of A. So this is a pure solution. Remember, this is the left-hand side of my osmotic chamber that I showed, or the big bath. Okay. We recognize R here instead of KB, so we are definitely working per mole. Okay, this is your telltale sign. Now, if we have a liquid in equilibrium with the gas, if it's in equilibrium, we know that the mu's are the same. That means that if they are the same, that means that the right-hand side are the same, so we can write it this way. Okay. Now, suppose that we mix B into liquid A, so the mole fraction of A is going to be reduced, right? For a pure system, by definition, the mole fraction for a pure system, the mole fraction is 1. Is the number of moles of that structure of that molecule compared to the total molecule. But since the only molecules is A, X, the mole fraction for those pure substances is 1. If I add something to the solution, automatically XA will go lower than 1, okay? And we are going to increase XB, and of course XA plus XB will be equal to 1 because we have the total molecule there, okay? So now that we've done this, we're still in equilibrium. This is a different equilibrium, but we are still in equilibrium between the liquid and the gas. I mean, this equilibrium is different, but it's still an equilibrium. And you notice the difference between the notations here is that we dropped the asterisk. And we dropped it because we are no longer in a pure substance. This equation here works when I have molecule B that are dissolved into liquid A. And of course, the right-hand side is still correct, but we have replaced the actual partial pressure PA in the solution, right? We dropped the asterisk since we no longer have a pure substance. So we can write this, and we know we are in equilibrium between the liquid phase and the gas phase. And of course, that means that we can write now that by substituting, we can substitute this term here, okay? So we can substitute this term by mu AL star minus RT ln PA star over P phi. We can substitute that here. And of course, properties of the logarithm, I can simplify. I end up with this important equation that the chemical potential of the solution A in presence of B is equal to the chemical potential of the pure solution A plus RT ln of the relative the ratio between the partial pressure of molecules A divided by what they were when it was a pure substance. So far so good. Now we can keep moving, and we have here to remember Raoult's law, and I'm not going to prove it here, but it says, and I think it makes intuitive sense, that the partial pressure A in presence of another molecule like B is actually the same as the pure, but normalized by the pure pressure, normalized by the mole fraction. Okay, so if the mole fraction x equal to 1, of course, the pressure will be equal to PA star. If XA is equal to 0, so you no longer have molecule A, of course, PA equal to 0. So that's just two limiting cases that seems to work, but it makes intuitive sense. That will allow me to replace PA over PA star, PA asterisk, by XA, right here. So that's exactly what I have. So basically, we found that the chemical potential of A has decreased, right? So the chemical potential of A, right here, is what it was before, plus a term that involves the logarithm of a number that's less than 1. The logarithm of a number that's less than 1 is negative, so the new chemical potential went down. Okay, that's what happened. So during this, the dissolution of by the fact that we're adding molecule B in A, we have decreased the chemical potential. So this is my A plus B solution. So now try to think a little bit about, and I may have that on this next, yeah, it's perfect. So let's try to, before we go any further, by having A plus B, we have decreased this chemical potential, right? We just saw it. We have decreased it compared to what? Well, compared to this, okay? Now, we know that if you put two systems together that can exchange particles, they will try to have the same chemical potential on both sides. This is minimization of Gibbs function. Now, we have created asymmetry between the chemical potential. So what happens? Well, the way to solve this is to get rid of B's, right? If you could get rid of B's here, you would increase the chemical potential. But the problem is that you can't do it because it's semi-permeable permeable membrane that does not allow you to get rid of B. You are stuck with B on the right-hand side. So how do you fix this? Well, the other solution, if you go on the previous slide, is to increase XA. How do you do that? By moving particle from here to here. So by moving particle from here to here, you are going to increase back again the chemical potential here, so until the two chemical potential on both sides are the same. So this explains the osmotic pressure. Let's try to get this a bit more numerically now that we understand what's happening. Okay, so I said all this already, so I don't have to say it again. We need to make sure that at equilibrium, the chemical potential here and the chemical potential here will be the same. This is what happens after the exchange of particles. So in other words, I can write the new chemical potential, the chemical potential would be equal to this, and we know that this chemical potential, we just calculated on the previous slide, this chemical potential at the new pressure is the chemical potential of the pure substance, right? We've done this before, plus the correction, which is what we did on the previous slide. Now, how does the chemical potential vary with pressure? Because remember, what I'm interested in is the pressure. So we need this. Well, of course, this is where we remember that we have yet again a magic relationship from all the work we've done that gives us this variation of the Gibbs function as function of pressure, and we know that the Gibbs function is the chemical potential per particle, and this is actually giving me the volume. So now that allows me to write the variation of the chemical potential as a function of volume, and of course I integrate this, the integral here will be giving me the difference of chemical potential between P plus pi and P, okay? Now, we are going to make an approximation here. We are going to suppose that in that range of pressure, the volume of A does not change much. Of course, it changes a little bit, but let's suppose it doesn't change much. So in other words, we are going to suppose that VA is a constant, and all I'm going to have left here is VA times pi. So that will allow me to rearrange all this and use this equation to write that the chemical potential here is equal to this thing here, right? So just convince yourself going from this equation to this equation to this one. And then, of course, these two terms are the same, and that's going to give me a description of the pressure. So the pressure that you have, the osmotic pressure times the volume, is minus RT ln XA, XA being the concentration of A in the solution here. So that gives me essentially the pressure. And again, how did I was able to do this? even though I had a hard time to find the pressure dependence, well, I remember one of those relationships from the Gibbs energy. So we are almost there. We're almost there. Let's try one more thing. Because what I'm really interested is to do this as a function of the amount of B molecule, not so much A molecule. So first of all, the total number of moles does not change, so XA plus XB is equal to 1, and we know that the amount of B is very small. We just have a tiny fraction of B inside the solution. That means that the ln of XA is equal to essentially ln to 1 minus XB, right? I replace XA by 1 minus XB. Why did I do that? Well, because for those who paid attention in courses where you studied Taylor series, the ln of 1 minus a tiny number, there is a Taylor series for this. Ln of 1 plus or minus a tiny number, if we stop at the first order, we just get a linear term. So this term here, minus without the minus, will be equal at first order to minus xb, since xb is so small. So in other words, putting all this together, minus ln xa is actually almost equal to xb from this. And that allows me to replace this minus ln xa by xb. So and I get this equation. I'm almost there, not quite, but almost. Now, I remember also that the fraction xb is the density of B molecule over the entire density of molecule. I also know that the total volume here is essentially the density of A times VA. It's not exactly the same because, of course, we have this is an approximation here. Okay. And then, of course, the density of B is much smaller than density of A, which is another way of saying this. All right, good. So that means that if I put all this together, it turns out that VA is V over NA. VA is V over NA, yeah. Okay, but NA is essentially XB times NB. Okay, so basically XB is pretty much NB divided by NA, since NA plus NB is almost equal to NA, right? That's the idea. There are many more, and so I can replace NA plus NB by NA. So XB is NB divided by NA. So I replace it here. XB becomes NB divided by NA. But NA times VA, and I moved NA here, so NA times VA is V, and then I'm done. So basically the pressure, the osmotic pressure, is given by the density of B molecule times RT over V. And this is essentially how you calculate the osmotic pressure that we need. That was a very long screencast. That's a very long lecture. There's a lot to unpack. I'm not going to go through the summary. The summary page is here. You can stop it and read it. The main thing is that we had to introduce basically a new term, mu dn, and the chemical potential. And we just had to rework all the math and introduce a new ensembles, and this was a grand canonical ensemble. And by doing that, we were able to understand all those processes where we have that are thermodynamic processes, but where we actually can exchange a number of particles, or we can exchange the type of particles. And that allowed us to also understand the osmotic pressure and the osmotic force, which is not a force that's due to the change in energy, but it's due to the fact that the system is trying to maximize the entropy. I would like to thank you for your attention on this very long screencast. Thank you.